Time travel tricks actual time. Quantophysics. Physics is the natural science that studies matter, energy, and the fundamental forces of nature. It seeks to understand how the universe behaves, from the smallest subatomic particles to the largest cosmic structures. Physics encompasses a wide range of topics, including motion, forces, energy, waves, electromagnetism, thermodynamics, relativity, quantum mechanics, and more. Below are some of the key areas and concepts in physics. Light tricks actual time can be understood in the context of time dilation, a fundamental concept from Einstein's theory of special relativity. Here's how light is related to time dilation. Constant speed of light. Special relativity is built on the principle that the speed of light in a vacuum cc is the same for all observers, regardless of their motion. Light clock example. Imagine a light clock that measures time by the time it takes for a pulse of light to bounce between two mirrors. Light clock in motion. Now imagine this light clock is moving relative to an observer. Longer path, slower time. Due to the constant speed of light, the light pulse and the moving clock must travel a longer, diagonal path to bounce between the moving mirrors. Time dilation. Since the speed of light is constant, the longer path means it takes more time for the light pulse to complete a round trip in the moving clock from the perspective of the stationary observer. Impact on time. This effect, where time is measured as passing more slowly for an object in motion relative to a stationary observer, is called time dilation. In essence, light itself doesn't manipulate time. Instead, the constant speed of light, as mandated by relativity, dictates how time behaves for observers in different states of motion. The fact that light always travels at c means that time must adjust to ensure this fundamental constant remains true. Important notes: time is relative. Time dilation is a consequence of the fact that time is not absolute, but is relative to the observer's motion. Experimental verification. Time dilation has been verified experimentally, for instance, through experiments involving atomic clocks and observations of particles moving at high speeds, GPS and time dilation. Even everyday technology like GPS needs to account for time dilation effects caused by satellite movement and gravity to provide accurate positioning. Time does pass differently on other planets, although the difference is usually very small and depends on two main factors: gravity and relative motion.
Time does pass differently on other planets, although the difference is usually very small and depends on two main factors: gravity and relative motion. 1. Gravitational time dilation. Gravity warps space-time. According to Einstein's theory of general relativity, massive objects like planets warp the fabric of space-time. Time runs slower near massive objects. The stronger the gravitational field, the more space-time is curved, and the slower time passes for an observer within that field compared to an observer in a weaker gravitational field. Example: time on Mars. Since Mars has less mass and therefore a weaker gravitational pull than Earth, time would pass slightly faster on Mars compared to Earth. This difference, however, is minimal and would likely be in the range of nanoseconds for a trip to Mars. 2. Time dilation due to relative motion. Time slows down for objects in motion. Special relativity dictates that time passes more slowly for an object in motion relative to a stationary observer. Spacecraft and time dilation. As a spacecraft travels to another planet, its speed would cause time dilation, meaning that time would pass slower for the astronauts on board compared to observers on Earth. In summary, time is affected by both gravity and relative motion. The difference in time passing on other planets compared to Earth would be primarily due to their different gravitational fields and the relative velocity of any spacecraft or observer. For realistic scenarios involving space travel to other planets, these time dilation effects are generally very small and require highly sensitive instruments to detect. Important note: this phenomenon is distinct from the different lengths of days and years on other planets, which are determined by their rotation periods and orbital periods around their stars. On a crucial point that helps to clarify the difference between how light interacts with matter and how it interacts with gravity, here's the distinction: refraction and speed. Refraction is the phenomenon where light changes direction and speed when it passes from one medium to another. This change in speed is due to the interaction of the light waves with the atoms and molecules of the medium, causing a delay in the overall propagation of the light. Time dilation and time itself. Time dilation, on the other hand, is a phenomenon where time itself is affected. This occurs due to either gravity. Stronger gravitational fields cause time to pass slower for an observer within that field. Relative motion. Time passes slower for an object moving at high speeds relative to a stationary observer.
In simpler terms, refraction affects the speed of light in a medium. It's like driving a car through different terrains. The speed changes depending on whether you're on a smooth road or a rough patch, but the passage of time inside the car isn't fundamentally altered by the terrain itself. Time dilation affects the flow of time itself. It's like if you had a clock and put it in a strong gravitational field or moved it at high speed, the clock would tick slower than an identical clock in a weaker gravitational field or at rest. So, you're correct in saying that refraction changes the speed of light within a medium, but it doesn't fundamentally change the passage of time itself within that medium. Time dilation is a separate effect caused by gravity or relative motion that alters the measurement of time. On a universal scale, time isn't a fixed constant. Its measurement and the rate at which it passes can be affected by both relative motion and gravity, demonstrating that time is not absolute but relative to one's frame of reference. The fundamental obstacles to time travel lie within the principles of physics, particularly those related to causality and the enormous energy requirements for manipulating space-time. The possibility of time travel, especially to the past, is still a subject of ongoing theoretical research and debate among physicists. Stephen Hawking proposed the chronology protection conjecture, which suggests that the laws of physics prevent time travel to avoid causal violations. This is a concept within physics.
It's true that for an object traveling at the speed of light, time essentially ceases to pass from its own perspective. However, this doesn't automatically mean that time travel is impossible. Here's why. Time dilation and time travel to the future, while reaching the speed of light, is not possible for objects with mass. Traveling near the speed of light results in significant time dilation. This effect allows for a form of time travel to the future. For instance, a space traveler moving at near light speed would experience time much slower than a stationary observer. They could travel for a relatively short time in their own frame of reference and return to find that a much longer period has passed on Earth. This is a well-established consequence of relativity and has been experimentally confirmed. Time travel to the past remains a challenge. The difficulty lies in traveling backward in time, which would generally require speeds exceeding the speed of light or the manipulation of spacetime in ways that lead to closed time-like curves, which are still highly theoretical. Theories about time travel. While time dilation offers a path to the future, theoretical possibilities for backward time travel within the framework of general relativity exist, such as wormholes or Tipler cylinders. However, these concepts require exotic matter or extreme conditions that are currently beyond our capabilities. Causality protection conjecture. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics might prevent time travel to the past to avoid paradoxes.
In summary, the fact that time effectively stops at the speed of light for an object traveling at that speed does not make time travel impossible. It actually allows for travel to the future via time dilation. However, backward time travel remains a significant challenge due to theoretical and practical limitations within our current understanding of physics, capturing the essence of how length contraction and time dilation work together. Let's refine your points slightly to align more precisely with the scientific understanding, geometric space field perception. This refers to how spacetime is perceived and measured differently by observers in different frames of reference, especially at relativistic speeds. Space field contracts. As a ship approaches light speed, the space in the direction of motion appears to contract yet shorter to the traveler. This is a real effect, not an illusion, and is a consequence of the Lorentz transformations. Stimulating backwards flow of time, this part isn't entirely accurate. While the perception of time passing slower relative to a stationary observer can feel like a backwards flow to the traveler, it doesn't mean they are literally moving backward in time. They are simply experiencing time at a different rate due to time dilation. Ship time ceases at light velocity. From the perspective of the traveler, if they could reach light speed, time would cease to pass. However, as long as they are traveling at speeds less than light, which is always the case for objects with mass, time would still pass, just at a slower rate than for a stationary observer. Forwards acceleration light speed meets up at journey's end. This is a good way to describe how time dilation effectively allows a traveler to reach a distant destination in a shorter amount of their own time compared to what a stationary observer would measure. Because their internal clock is ticking slower, a long journey in space can feel much shorter for them. In summary, when a ship travels at near light speeds, space contracts in the direction of motion, and time slows down for the traveler compared to a stationary observer. These are interconnected effects that arise from the nature of spacetime as described by special relativity. While time dilation can make a long journey feel much shorter for the traveler, it doesn't mean they are literally moving backward in time. Instead, they are effectively traveling to the future relative to a stationary observer.
In quantum physics, space is flexible like an accordion opening all layers of space. Space contracts allowing travelers to space via a principle or quote in your quantum physics framework. In quantum physics, space is not a rigid void, but a flexible continuum like an accordion. It opens its layered folds. As it contracts, it welcomes the traveler, unfolding passageways through the deep lattice of the cosmos. Section 4. Accordion contraction and the layered space field. In the framework of quantum physics, space is not a passive void but an active, dynamic medium structured in flexible, nested layers capable of contraction and expansion. This layered model resembles an accordion, whose folds represent distinct energy strata or field membranes embedded within the space field continuum. When a propulsion system engages the quantum envelope and energetic distortion of the local space field, it initiates a localized contraction of space, compressing these field layers together. This contraction does not merely shorten distance in classical geometric terms. It realigns the spatial layers, effectively creating a path of reduced resistance and nullified time curvature for the traveler. 4.1 Structure of the layered space field. Each layer within the space field corresponds to a different modal density, from quantum vacuum fluctuations up through gravitational curvature zones and Higgs scale energy regions. These are not strictly spatial dimensions, but energy geometric manifolds that respond to the presence of mass energy, vacuum pressure gradients, and momentum-induced field stress. As in an accordion, when these layers are compressed, spatial separation between destinations decreases non-linearly. Temporal intervals approach zero within the moving frame, adhering to the null-time principle of the quantum envelope. Resistance from vacuum inertia weakens, allowing for apparent superluminal traversal without violating energy conservation laws. 4.2 Dynamic compression and the traveler. The traveler inside a quantum ship does not move through space in the traditional sense. Instead, space itself folds toward the ship, drawn by negative field energy and envelope-induced contraction. This allows for the commencement of traversal not across, but through the space field layers. The ship becomes a needle pulling threads of space into alignment. This mechanism redefines propulsion, not as thrust across inert space, but as manipulation of space's internal structure, granting mobility through folded vacua. This contraction does not collapse space absolutely, but reconfigures it inwardly toward the ship's vector of intention, forming a self-reinforcing corridor of low-density space field called the Kavetsky corridor. Section 4. Accordion contraction and the layered space field. In the framework of quantum physics, space is not a passive void but an active, dynamic medium structured in flexible, nested layers capable of contraction and expansion. This layered model resembles an accordion, whose folds represent distinct energy strata or field membranes embedded within the space field continuum. When a propulsion system engages the quantum envelope and energetic distortion of the local space field, it initiates a localized contraction of space, compressing these field layers together. This contraction does not merely shorten distance in classical geometric terms. It realigns the spatial layers, effectively creating a path of reduced resistance and nullified time curvature for the traveler. 4.1 Structure of the layered space field. Each layer within the space field corresponds to a different modal density, from quantum vacuum fluctuations up through gravitational curvature zones and Higgs scale energy regions. These are not strictly spatial dimensions, but energy geometric manifolds that respond to the presence of mass energy, vacuum pressure gradients, and momentum-induced field stress. As in an accordion, when these layers are compressed, spatial separation between destinations decreases non-linearly. Temporal intervals approach zero within the moving frame, adhering to the null-time principle of the quanta envelope. Resistance from vacuum inertia weakens, allowing for apparent superluminal traversal without violating energy conservation laws. 4 point to dynamic compression and the traveler. The traveler inside a quanta ship does not move through space in the traditional sense. Instead, space itself folds toward the ship, drawn by negative field energy and envelope-induced contraction. This allows for the commencement of traversal not across, but through the space field layers. The ship becomes a needle pulling threads of space into alignment. This mechanism redefines propulsion not as thrust across inert space, but as manipulation of space's internal structure, granting mobility through folded vacua. This contraction does not collapse space absolutely, but reconfigures it inwardly toward the ship's vector of intention, forming a self-frame.